Greetings, aspiring scientists. It's been quite a while since my last video. A lot of things going on in my personal life. I took a 2-week trip to Canada, Victoria, with some of my students for like leadership summer camp training. I moved to a new apartment, so this is my new room for making videos and doing work and stuff. And then I also took an IB workshop for ESS, Environmental Systems and Societies. So if you're taking that class, I know a little bit about what you're doing now, and I can make connections with chemistry and physics and the other classes I already know. So that's cool. But where we left off with my lessons was Reactivity 2, specifically rates of reaction. So that's what we're going to be doing today. So this is Reactivity 2.2, how fast the rate of chemical change. Let's go to my slides. So we do have a guiding question for this section. That is, how can the rate or the speed of a reaction be controlled? We would want to do this for many reasons. We want things to go at sort of an optimal speed, not too fast, not too slow, not so fast that there's an explosion and a sudden release of energy, but not so slow that nothing ever happens in our lifetime, kind of thing. So how are we going to control that? We're going to try to learn in this topic. So 2.2.1, sort of an introduction to what the rate of reaction is. So here's some interesting questions that you can ask about any chemical reaction to determine its usefulness and properties about it. So number one, what occurs during the reaction? And we're mainly going to answer this with stoichiometry and the balanced equations, balanced chemical equation. What becomes what? And what are the fractions at which things need to combine and get produced at? So we can make predictions. Next, number two, what's the extent of the chemical reaction? So after you have a balanced chemical equation, you have to ask, does this actually go 100% or not? Maybe it only goes, 75% of the starting materials become those products, 50%, 25%. How does it go? So we'll mainly answer that with equilibrium. That's in a future topic. And spontaneity is kind of an HL topic related with equilibrium as well. But to answer this, basically everything goes to the lowest energy point on a kind of mathematical plane or graph. Third then, does the reaction happen rapidly or slowly? And is it dangerously fast or unrealistically slow? So like I said, we don't want an explosion release of energy and pressure usually. And we don't want unrealistically slow. We want things to happen in kind of seconds, minutes, hours time frame usually. And number three here is what's really related to the reaction rate. So that's what we're focusing on in this topic. And number four, what energy transfer is involved in the reaction? That's thermodynamics and enthalpy. So we're going to get an exothermic or endothermic reaction. And how many joules of energy will be released or consumed. We've already talked about that earlier on. So rate, we're really going to focus on this moving forward in this topic. So we can define the reaction rate as an amount of product change per unit time. This is very much related to rates of change and derivatives from math. So if you've already talked about rates of change in math or calculus, derivatives, you'll be very much at home with chemical reaction rates. Now, since we live in a 3D space, we usually want to include the volume that our reaction is happening in our definition. So when we choose our amount of product change, we could choose grams or moles or whatever, even volume, but the most standard definition of reaction rate is going to be concentration. So a moles per decimeter cubed per second. And we write it like this. I have in the middle of this slide, reaction rate in mole per decimeter cubed per second, written with the Greek letter nu. Okay, it's not a V, but nu equals the absolute value of the change in concentration over change in time. Time taken for that change in concentration. So we just put the absolute value there because we usually don't want to talk about rates as being negative, right? A rate of change you can think of as just being a positive kind of magnitude. All right, now the reaction rate cannot be negative. We take the absolute value of that concentration change. However, the observed concentration can be a reactant decreasing. That will give you a negative delta C on the top, but then we just take the absolute value of that. It can also be product forming. That will already be positive, so when we take the absolute value, there will be no change to it. And this definition I've written in the middle of this slide really is what we can call the average rate over some time frame, delta t. You can also ask, what is the instant rate at some specific instant in time? For example, at exactly 5 seconds after the reaction started, what is the rate of change in mole per decimeter cubed per second? You can answer that with mathematics and graphs. That's known as the instantaneous rate at some time. And it's more clear to write that as dc, absolute value, by dt, where the d's are like from calculus. It's the same kind of idea as delta as a change, but this d is a sort of infinitely small change. So an infinitely small change in concentration over an infinitely small time period is what we will call the instantaneous rate. Okay, so now to break this down to different parts of a chemical equation, if we use this kind of example, XA plus YB goes to QC plus PD, you can just imagine this as A, B, and C and D are some chemicals. A and B are the starting materials, C and D are the products, and then the little letters X, Y, Q, P, these are the stoichiometric coefficients, the kind of things we would use for mole ratios. It tells you how many atoms or how many moles are required or produced. Now, there exists a relationship where you can find the rate with respect to each part of this equation. You can find a rate for A, a rate for B, a rate for C, and a rate for D. And if they are all 1-to-1 ratios, all stoichiometric coefficients of 1, they will all have the same rate compared to each other. But if there's any kind of stoichiometric coefficient, like 2a plus 3b goes to c plus 3d or something, where all those x, y, q, and p are different, suddenly individual species in this will have a different rate than the overall rate. And one way that we can bring them together back to a same constant, consistent number is by multiplying each individual rate by 1 divided by the stoichiometric coefficient. Okay, so for example, if x is equal to 2, so we have 2a plus b, c, d, we would take 1 over 2 multiplied by the rate of change of a, and that will give us the overall rate for this chemical reaction. Okay. Mathematically, these things just obey this rule that I'm showing you here, but it kind of makes sense, right? Like if we need to make 1 unit of C, we consume 2 units of A, we're going to observe A disappearing faster than C appears, but it doesn't really mean that the overall rate of the reaction is going faster, right? It's really kind of the overall rate that you want to find in the end to find out how fast things are going overall, instead of just looking at one particular species in your balanced chemical equation. There are cases where you would do that, but in most of the cases we're going to look at here in my slides, we're going to be looking at the overall reaction rate. So some notes here. As I said, in the case where everything has 1-to-1 mole ratio, all the reactants are consumed and all the products are produced at the same rate. So you don't have to worry about this individual versus overall rate thing. However, if there are stoichiometric coefficients, x, y, q, p, those will affect the rates at which species change relative to others. So multiplying each individual rate, we can just say dx by dt, absolute value, where x is one of these a, b, c's, or d's in the chemical equation. Multiply that by 1 over its stoichiometric coefficient. This will get you the common rate known as the overall rate. And there is some vocabulary or phrasing to go with this. So the individual rate of any species X is usually expressed as the rate with respect to X. Okay, so you might say the rate with respect to water, or the rate with respect to CO2, the rate with respect to HCl. Those are the individual rates, the appearance and disappearance of those individual species. But if you say the overall rate, you're talking about the whole process, and you can find individual rates from that overall rate, but that overall rate might not even appear in any of the individual species. So just be aware of that, just be careful. So we'll do some practice with that, I think. Practice 1, consider this reaction. 2N2O gas goes to 2N2 gas plus O2 gas. So we have a ratio of 2 to 2 to 1. We're going to have to worry about individual rates versus overall rate. Okay, so under certain conditions, the concentration of nitrogen 1 oxide in the reaction mixture decreases by 0.2 mole per decimeter cubed over 10.0 seconds, producing 0.2 mole per decimeter cubed of nitrogen and 0.1 mole per decimeter cubed of oxygen over the same period of time. Calculate the average rate of reaction in mole per decimeter cubed with respect to each of the 3 species, 1 starting material, 2 products, over these 10 seconds. And we will do 10.0 just to make sure we have enough sig figs. So what to do, set up a couple equations, but make sure you label things very carefully. So we want to find the rate with respect to each species. We'll start with N2O, the starting material. So rate N2O. So this is equal to the change in concentration, absolute value, over change in some time period. And we can see that basically this starts at 0.2. Well, we don't know what it starts at or what it finishes at, but we know the change over this time is a decrease of 0.20 mole per decimeter cubed. And we will divide this by the time taken, that is 10.0 seconds. So this will come out to 0.020 mole per decimeter cubed per second. That's the way you can say this. Mole on top, decimeters cubed, and seconds on the bottom. So that is the rate with respect to N2O. Okay, let's do the next one, N2. But N2 and N2O have the same mole ratio, so this will be essentially the same, but instead of disappearing, N2 is produced, so this is positive. Doesn't really matter though, because we're taking the absolute value. And this again was done over 10 seconds. So it's the same, 0.020. Mole per decimeter cubed per second. Oxygen, though, I think we'll find is slightly different because of its different stoichiometric coefficient. So instead of 0.2 being produced, only 0.1 of oxygen was produced. Mole per decimeter cubed. This was also done over 10 seconds. So this comes out to half the rate, right? Right, compared to the others. (0.010). All right, and the second part of this question, part B, asks us, what's the overall reaction rate for this? So the overall reaction rate we can label this new overall. Well, this is equal to 1 over the stoichiometric coefficient of the N2O rate. It is equal to 1 over the stoichiometric coefficient of the N2 rate. And it is equal to 1 over the stoichiometric coefficient of the O2 rate, but that is just 1 over 1, so it's actually just equal to the O2 rate. And we know that. That was just what we did as the third part of part A. That was 0.010 mole per decimeter cubed per second. Okay, so if you ever find the individual rate of something in the balanced chemical equation that has a stoichiometric coefficient of 1, that is equal to the overall reaction rate. But if it has any stoichiometric coefficients, you need to consider that. So you can see that if you're going to solve for the individual rate of N2O or N2 using this equation I wrote at the bottom, it should be true that, I'll write it here, the rate of N2O, for example, is equal to 2 times the rate overall, which is 2 times 0.01, which is 0.020, same as somebody calculated in the lab. Don't have space to write the units there, but that should be fine. So that is the same as somebody measured in the lab here, right? Which it must be. Okay, moving on. Practice 2, under certain reaction conditions, ammonia can be oxidized to nitrogen 2 oxide. 4NH3 plus 5O2 goes to 4NO plus 6H2O. Over 5 seconds, the concentration of nitrogen 3 oxide in the reaction mixture increased from 0 to 6 times 10 to the minus 3 mole per decimeter cubed. Okay, calculate the rate with respect to NO and O2. All right, so that's one product and one starting material. And I should mention, we're finding the average rate here over 5 seconds and not any kind of instantaneous thing. So the rate of NO first with respect to NO. This will be equal to the change in concentration, absolute value, over a change in time. And we know that NO increased from 0 to 6 times 10 to the 3. So we can just set that as our delta C. And this happened over 5 seconds. So that will come out to about 1.2 mole per decimeter cubed per second. All right, then we have to find O2. We don't know anything about the rate with respect to O2 from the data given in this question, though. So I'm actually going to immediately recommend go to part B instead of finding the rate with respect to O2, because I think we'll need this. So part B, the overall rate will be equal to 1/4 the rate with respect to NO, because NO's stoichiometric coefficient is 4. All right. And why are we doing this? Well, the rate overall will also be equal to 1 over 5, the rate of O2. So that's what we'll use later on to find the rate with respect to O2. But here, if we want to find the overall rate, we need to take 1/4 times the rate with respect to NO, which we found in the first part there. That was 1.2 mole per decimeter cubed per second. So 1/4 of that is 0.30 roughly. Very useful, because now we can say the rate with respect to O2, just multiply both sides of that equation on the left by 5, is 5 times the overall rate. So 5 times 0.30. And that will give us 1.5. Mole per decimeter cubed per second. And that should make sense, right? Every time one of these processes happens, 5 units, either moles or atoms or whatever, of O2 will be used up to make this process proceed forward. Compare that to only 4 of NO being produced. So the rate when you look at NO looks like 1.2 mole per decimeter cubed per second, but if you look at O2 being consumed, it's slightly faster, but they are linked together through the overall rate of 0.3 mole per decimeter cubed per second. Okay, good. Moving on. So measuring reaction rates. I just want to mention how you might actually do this in the laboratory, because it's very difficult to measure concentration directly. So measuring concentration directly, counting the amount of particles in a 3D space is fairly difficult. But there's many things that are proportional or have a relationship with concentration that can be easily measured. You can measure a change in pH. Once you do the acids and bases section of this course, you'll learn that pH is not proportional, but has a direct relationship, a logarithmic relationship with H plus concentration or OH minus concentration. So if you have a reaction mixture where the acidity, the H plus or the OH minus, is changing, you can use the change in pH. Number 2 then, change in conductivity. So if you're measuring how well your solution transmits an electric current, you can do that. If you have a change in cation, something positive, or anion, something negative concentration changing significantly, you can use that to measure a concentration change. Third then, change in mass or volume, probably one of the most common ones. If you have a mass changing or a volume changing, for example, a gas being produced or a solid losing material that might be becoming a gas, we can measure changes in mass or volume. Those are proportional to concentration. And then change in color, significant absorption. If you have absorption at some wavelength, either usually visible or ultraviolet. I think you can do almost any part of the electromagnetic spectrum, but the most common one is UV vis, ultraviolet and visible light. Those will be proportional to concentration change as well. So here's an example. Maybe we have some calcium carbonate, and we're adding some hydrochloric acid, HCl, onto there. So we would have a flask. We put our calcium carbonate in after measuring it, and we dump in some acid, HCl. Then we stopper it, but we leave a little tube where we can capture any gas that's building up and measure its volume in a separate container. So we have a delivery tube, water to make sure we're capturing this volume and able to read it. And then we have a graduated cylinder clamped, and our CO2 bubbles come in. We can measure a volume there. And we can generate a graph from this. If we take a measurement every few seconds, maybe every 10 seconds here, you can see we can graph this. So at 10 seconds, there was 20 centimeters cubed produced, 20 seconds, 30, 30 seconds, 37.5, and this goes on. And then it looks like at about 70 seconds, there stops being any increase. So we can say that the reaction is done. It's finished at that time. There's no more change. So from this graph that I've just shown, you can get a lot of information. You can get the average rate of reaction. For example, it looks like the reaction finishes at 70 seconds, right? So what you want to find basically is the slope of a line that goes from the start, 0 seconds, up to 70 seconds. Slope of such a straight line. Okay, you don't even need to make the graph to really do this, but I'll show you mathematically what it might look like. So the average rate, and this is with respect to CO2, right? A specific product being produced. This is equal to, now we don't know like what kind of volume of solution this was in, so we can't find mole per decimeter cubed, but we can find something related to that, which is delta V, change over time. So we went from 0 to 53, you can see in the table below. "53 centimeters cubed, and how much time did it take? It took 70 seconds. So this can give you a rate of 0.76 centimeters cubed per second, roughly. Okay, if you want to find that in terms of a concentration, you kind of need this volume of HCl that was added. I'm sure we'll see that in an example soon. But for now, what we can get from this graph and this data set is a production of gas, centimeters cubed, volume per second, on average over the course of the entire reaction time. So very similar to what we did previously, just showing this graphically here. And this is with respect to CO2, but remember CO2 has a stoichiometric coefficient of 1 or nothing there. So this should be the overall reaction rate in terms of volume as well. Okay, good. Practice 3. An experiment was carried out using a piece of magnesium ribbon and 0.1 decimeters cubed of 0.25 mole per decimeter cubed hydrochloric acid. Hydrogen gas is released. The volume of gas released was recorded every 10 seconds until a constant reading was obtained. These are shown in the table below. So very similar, time on the top here, every 10 seconds, a measurement of volume was taken, and this is the volume of H2 produced. So we have some things to do. A, calculate the average rate of reaction in mole per decimeter cubed per second with respect to H2 for the following intervals, from 0 to 10 seconds, and then between 0 and the end of reaction. Assume SATP, standard ambient temperature and pressure. So that is 25 degrees C and 100 kilopascals. I'm pretty sure that's in your data book. And calculate the overall rate of reaction for the whole reaction time. Okay, so there are some things to do here. It's more complicated than it seems, I think. So I think first what I would like to do is find out for this 0 to 10 seconds how many moles of H2 was produced. So I'm going to use ideal gas law. Unfortunately, this is not at STP, so we can't use the molar volume of 22.7 that I would usually use. But we can use PV equals nRT. And then our moles of hydrogen is equal to PV over RT. And we've got SATP, that's 100,000 pascals for pressure. we've got a volume, and now the volume that we want to use here is the volume of gas that is produced over the changing volume period. So in the first 10 seconds, 111 centimeters cubed. But to use PV equals nRT, we need meters cubed. So I'm just going to quickly convert that into meters cubed. It's 0.000111 meters cubed. We need to do that because we're working with the ideal gas constant R. That's 8.314 joule per Kelvin per mole. And then temperature 25 C for SATP, that is 298 Kelvin. Okay, so put that in your calculator. You should get that. That's about 0.0448. 0.0448 mole of H2 produced over the first 10 seconds there. So if I want to find the average rate with respect to H2, this is going to be absolute value of change in concentration over change in time. So this will be absolute value of moles, 0.0448. Now, this concentration is moles per volume, right? C equals N over V. What V to use there? You don't want to use the volume of H2 produced, but what you want to use, and this often trips a lot of people up, is the volume of the reacting part of your apparatus and the mixture. So it's the liquid on top of the solid that's really going to be where most of this reaction is taking place. So that is 0.1 decimeters cubed. And now we want our rate to be in mole per decimeter cubed per second. So I will just use this as it is, 0.100 decimeter cubed. So that will give us a concentration, which we need, and divide this by the time. That is 10.0 seconds. I know these times in the data table here don't have those 0.0, but let's just imagine for a significant figure's sake that we have that. Okay, so put that in the calculator and we would get again 0.00448. Okay, we're dividing by 0.1, which is the same as multiplying by 10, and then dividing by 10. So essentially the number doesn't change from what we calculated for moles of H2. But that's not always the case, so please be careful. These do have units of mole per decimeter cubed per second then. Okay. Now that's the first time period, but then it says, please do that again for the time period 0 and the end of the reaction. So I'll just point out that you can find the number of moles produced there instead using this N equals PV over RT, but just set V equal to the total volume produced instead. So that's going to be 0.000248 meters cubed instead. And if you do that, I think you will get that moles of hydrogen here. Allow me to just separate these. So moles of hydrogen here will be 0.100. 0.0100. Okay, so if we want to find the rate with respect to H2 for the entire reaction time, we'll use the absolute value of 0.0100 mole over the same reacting volume, 0.100 decimeter cubed. All of that in the absolute value divided by the time. So the time for the whole reaction was 90 seconds. That's when there stopped being any change. So over 90 seconds. So that comes out to kind of out of space here, but I'll go left, 0.00111 mole per decimeter cube per second. Okay. Now calculate the overall rate of reaction for the whole reaction time. One thing we didn't do that we probably should have done is write a balanced chemical equation for this. I'll just write that at the top here. So we're working with Mg solid reacting with HCl goes to MgCl2. Have to be able to realize that this is what's happening, and then H2 gas. So balance this, we're going to need 2 HCl. But everything else is 1. So 1 to 2 to 1 to 1, and we found with respect to hydrogen these average rates. So the overall rate of reaction should be the same as H2. It has a stoichiometric coefficient of 1, so you would do 1 divided by 1 times 0.00111, but it ends up being just the same. So the answer to B is the same as the answer to A2. Okay, trickier than it looks. If you get a little bit faster, you can do that faster than I did, I'm sure. All right, now what else do I want to say about this? So this is data we've looked at. CO2 being produced from HCl onto calcium carbonate. So you can find average rate by taking, total amount produced over some time, but you can also find instantaneous rate at some exact time t. And there's also the initial rate you'll often see. This is a special case where the instantaneous rate at time 0 is found. Okay, so for example, if you want to find the instantaneous rate, I'll switch to red. The instantaneous rate at time 50, for example. What you want to do is find the rate specifically at that time, and you can do this with calculus if you're an advanced university student, but in IB, we're just going to find this with a tangent line. So you should learn about tangent lines in math, but it's a line that only intersects your function at one point. So I'll try to do this at 50. I need a straight line only contacting that line here. I didn't do the best job because your line's not supposed to touch the graph at any more than one point. It looks like mine kind of goes in and then it comes out, right? But that's the idea of it. Find a line like this that only touches your graph at one point, and then find the slope of that line. And again, if you want to find the initial rate, that's just the instantaneous rate at 0, 0, at time 0. So you would find the slope of a line like this. This is instantaneous at time 0. And this is equal to what we call initial rate. So in summary, the average rate can be described mathematically with the following equation. Nu equals absolute value of delta C over delta T. The rate is the absolute value of the concentration change over the time taken for that change. The instantaneous rate can be described mathematically then with the following equation: nu equals absolute value of dc over dt. So this is also a change in concentration, but the d is like an infinitely small change, and the dt is an instance of time, an infinitely small change that basically happens at one exact time. All right, so here's a bit more mathematically in-depth example of what I drew previously. So find the initial rate of this reaction. This is CO2 being produced. This is dc by dt. Without calculus, you must find this with a tangent line at the point 0, 0. The y value might not necessarily always be 0. It is in this case because we're talking about products being produced, so there's 0 products at this time. So we need to first of all, draw that tangent line. It's already drawn there, the blue line, and then find 2 points on that tangent line so that we can get the slope. Finding the slope of a straight line is very important in this class. You should know that it's the change in y, delta y, over the change in x, delta x, which you can find with y2 minus y1 divided by x2 minus x1. The change in the rise over the change in the run, my math teacher used to call it. Rise over run. So in this case, we have 2 points, right? 0, 0, and then 20, 50. Okay, to get the slope of that, 50 minus 0, y2 minus y1, divided by 20 minus 0, x2 minus x1. And y has units of centimeters cubed, x has units of seconds, so this will be centimeters cubed per second, and it's 2.5 centimeters cubed per second. All right, so that's in terms of volume change per second. That's fine for now. Next, find the instantaneous rate at 50 seconds. To do that, you'll draw your tangent. Try to draw a straight line that touches the graph only at the time 50 point. So I've drawn it there, and then choose 2 points on that tangent line to try and get your slope. We'll take, again, delta y over delta x. So my points, 20, 39, and 50, 50. We'll take that. So we'll take y2 minus y1, that's 50 minus 39, and divide that by x2 minus x1, that's 50 minus 20. And that gives us 0.367 roughly, with units of centimeters cubed per second. So what do we notice? We notice the instantaneous rate at 50 is quite a bit lower than the initial rate, and this will almost always happen. I think I can say it always happens. The rate later on, instant rate later on, is always going to be lower than the initial rate because our starting materials start to disappear, so the reaction can happen less frequently. And you can see that just in the slopes. The higher slope at the start will become the flatter slope later on. All right, let's look at another example, HCl with magnesium. Again, here's some data. Determine the initial and instantaneous rate at 55 seconds for this reaction of magnesium metal with 0.1 decimeters cubed of HCl. So we get 2 data sets here. One has H2 volume produced, and the other has HCl concentration disappearing. Try this with respect to the disappearing HCl data first. Okay, so you would make a graph of this disappearing HCl concentration. So try this with disappearing HCl first. Here's what that might look like. We start with 0.250 mole per decimeter cubed, and then over time, every 10 seconds, we have a data point. All right, so we can find the initial rate from this in our favorite units of mole per decimeter cubed per second by just drawing a tangent line at that 0 time point. Okay, so if we want to find the initial rate, let's not forget this is with respect to HCl. So this will be equal to the absolute value of dc dt which we'll get from our tangent line. We've got tangent line drawn there, and we can take 2 points on it. I think we'll use the point 0 and 0.250. And the other will be 14 and 0.1. I'm just writing a bit of extra significant figures that you would usually be able to get from this graph. So here we're going to have 0.1 minus 0.25. And we have time 14 minus 0. And don't forget your units. This time is seconds, and this y values are mole, and this y values are mole per decimeter cubed. So this will give us 0.0107 mole per decimeter cubed per second. Initial rate with respect to HCl, changing concentration. All right. Now, do you remember the balanced chemical equation for this? It was Mg plus HCl goes to MgCl2 and H2 gas. And we had a 2 here, 2 HCl required. And that means the overall rate is equal to 1 over 2, the rate of HCl, which we just found, 0.0107. So it's about 0.00535. I don't think the question asked for that, but it's just good habit if you have time to find this. Could be useful later. All right, so the overall rate is half of what it would look like for the disappearance of HCl. This also said to find the instantaneous rate at 55. So I'm just going to clean this up a little bit. Okay, so for our rate at 55, with respect to HCl, this is going to come from our tangent line. It's already drawn here, T55. Tried to draw a straight line that only touches that graph at the point of 55 seconds. So we'll use some points for this. I've chosen these points. So the first point is 32.085. And the second point on that tangent line that we'll use to get the slope is 0.045. All right, so y2 minus y1, we'll take absolute value of 0.045 minus 0.085. And divide this by 78. I'm going to put these point zeros here, so we have 3 sig figs. Minus 32. And units here, 32 seconds, mole per decimeter cubed on the top. So that will come out to 0.00087. I guess I didn't need the zeros for sig figs. We'll just have to. .00087 mole per decimeter cubed per second. So does that make sense? It's a lot less than the initial rate, and as I said, that will usually be the case. I guess always be the case. We have the reaction slowing down as the starting materials are disappearing, and they are required to make the reaction go. So it gets slower over time. You can see that in the slopes. There's a steep negative tangent line at the initial rate, but then more flat at 55. So this makes sense. All right, and that's everything required there. So the next part is just to prove to ourselves something. Try to find the initial rate with H2 gas that's being produced. Again, assume SATP, 25 degrees C, 100 kilopascals. So we've already found the initial rate with respect to HCl, but I also want to find it with respect to H2 to show that the overall initial rate will actually be the same. So if we take instead the table on the left here and graph that instead, now it's going to be an increase. We get this instead, volume of H2 being produced. Now, first thing to do here, if we want to compare this with concentration of HCl, we need to convert this H2 into concentration as well. So first would be moles. Moles is PV over RT. So again, SATP means 100,000 pascals. Volume. Now we need to be a bit careful here. We're choosing a volume that's kind of a theoretical amount based on our tangent line here. So if our tangent line rate continued, how much volume would be produced at that point at 12 seconds? And it's 160 centimeters cubed, right? That sort of tip of the tangent line, that red point. So that is in meters cubed, 0.000160 meters cubed for our volume. And then R, as usual, 8.314 joule per Kelvin per mole. And temperature 298 K. But that will come out to give us 0.00646 moles. Of H2 based on that tangent line, the red line. Okay, so our initial rate, with respect to H2 will be equal to the absolute value of the concentration change. We go from 0 up to some amount, so we'll just take the amount that is produced, 0.00646 mole per. Now the volume needs to be the actual volume of the solution of HCl that's poured onto this solid. Again, I know this gets really confusing, but this volume is the reaction mixture, the part that's actually containing the reaction. So it is the liquid, the HCl. If we go to the previous slide, that was again 0.1 decimeters cubed of HCl. So we'll use that here, 0.100 decimeter cubed of HCl, the reaction mixture. Sometimes this will be the container that it's being done in, but for this case, It's the liquid. It's going to be reacting in the liquid acid. And then the time on our tangent line, this is like 12 minus 0, so it's 12 seconds. So this will come out to 0.00538 mole per decimeter cube per second, the best units for rate. That's why we did all that work, converting units. All right. So that's the initial rate with respect to H2. But again, we had our balanced chemical equation, Mg plus 2HCl goes to MgCl2 and H2. So our stoichiometric coefficient for H2 is 1, and that means same as overall rate. So the overall rate should be 0.00538 as well. Now, is that the same as what we calculated for the disappearance with HCl previously? And yes, basically it is the same. It's off by, a couple decimal points, but that's just rounding errors. Basically, this does show that you can use either the appearance of H2 or the disappearance of HCl. As long as you do everything in the correct units, you can compare the overall rates in the end, and overall rate should be a constant value. Does not depend on individual species, doesn't depend on which individual species you're looking at. Okay, so practice 4. Using this data set of calcium carbonate decomposing in a 1 decimeter cube container, plot the change in mass of the reaction mixture as a function of time. So this graph gives us delta M versus time. I don't really like thinking of it that way, although I think you can just graph this how it is and get the answers to B and C. I'd rather realize that this must have started as a 0.440 gram sample and then just subtract these at each time point. So I'll graph it like this. I'll start at 0.440 and then have it decrease over time based on those delta M decreases at each time point. So this is what my graph of that data looks like. I should say that the axis on the left is grams mass. So mass in grams is this axis. All right, now B, using the tangent line method, determine the initial reaction rate in grams per second. So I've drawn a tangent line here. I did my best to try to get that straight line that only touches this curve at the time 0 point. Okay, it's not exactly shown well here, but time 0 is here. This is also 0 grams, I think. Okay, so how to get that initial rate from this tangent line. And this is with respect to something. I'll talk about that in a second, but let's just do this from this graph. So initial, we need 2 points on this tangent line. I'm going to use 0 and 0.440 as the first one. And then 44 and 0.150 as the second point. So I'll write that in red on the actual graph as well. This point is 0, 0.440. And this one is 44, 0.150. Okay. Now we'll get our initial rate here as the absolute value, as the change in mass, 0.15 minus 0.440. These have units of grams. And this is over some time from our tangent line. It's going to be 44 minus 0. In seconds. Okay, so just here, this is equal to a rate in grams per second of 0.00659. And this question did just ask us for the rate in grams per second, so we can stop there. Part C then was determine the overall reaction in mole per decimeter cubed per second, the rate of the overall reaction. So what did we just find? This is with respect to something, right? But is it the overall rate? Well, it is the rate with respect to CO2. If we go back, this says calcium carbonate decomposing. So it's basically just being heated up and broken into several pieces. So that reaction we should know is CaCO3, calcium carbonate, goes to calcium oxide, which remains a solid, plus CO2. So everything's 1-to-1 here. So we found with respect to CO2, that will also be the overall reaction rate. But you might ask, why is this data with respect to CO2 if we're just measuring mass decrease? Well, we're measuring mass decrease, right? But that's only going to be because of CO2 gas that's leaving. It's not the calcium or the single oxygen in CaO that are causing this decrease. It's just CO2 gas leaving. That's why this is with respect to CO2 really that we're looking at. I think that's the best way to think about this. Because even though CaCO3 is our starting material, not all of that, not the calcium especially, is part of this decrease of mass. It's only due to CO2 leaving. So overall is the same. Also overall, we have a stoichiometric coefficient of 1. All right, now this does ask us to find units of mole per decimeter cubed per second, though. So what to do? We've got gram per second. Just let me clean this up a little bit. So gram per second, we need mole per decimeter cubed per second. I'm going to recommend that you multiply this by 1 over the molar mass of CO2. We know this is with respect to CO2. So 1 mole per 44.01 grams. This will cause our gram to cancel out. We'll have mole per second. And then if we look at the previous slide, we also had, this is done in a 1 decimeter cubed container. So we can take that as our volume. We can just divide by 1.00 decimeter cubed, which doesn't change anything. We end up then with 1.5 times 10 to the minus 4 mole per decimeter cubed per second. Okay, so we can do that just because we have a 1 decimeter cube container, and if we divide by the molar mass of CO2, we can convert grams into moles. Just a bit of dimensional analysis, but don't forget how to do that. All right, and then I think I have one more practice. Yeah, so this one involves absorbance, which is something you can measure at a particular wavelength. And this time it's done at 349 nanometers. I think that's UV maybe. UV or visible, but as I said, absorbance is proportional to concentration, and it's related through what's called the Beer-Lambert law. This says absorbance is equal to a constant, the molar absorptivity coefficient epsilon multiplied by the concentration multiplied by the path length, which is the container width basically that you're shining this light through. Now this is not directly part of the IB curriculum. It will show up maybe if you do some particular lab work or IAs, but this is one of the first things you would learn in university, I think. So what this means is absorbance is directly proportional to concentration, which is nice. So somebody measures in their instrument the absorbance after some number of minutes of a reaction that's happening. We don't really know what this reaction is, but we get the path length of 10 centimeters. We get the molar absorptivity coefficient of 4,700 decimeters cubed per centimeter per mole. Now, step 1 says convert all absorbances into concentration. You can do that, I think, fairly easily. Do something like C equals A over epsilon L. So if we just do the first one here, 0.43 absorbance units. Absorbance is a kind of unitless quantity usually. Divided by epsilon, that's 4,700. Centimeters minus 1, mole minus 1, decimeter cubed. So that will look like decimeter cubed per centimeter mole, like that. And then the path length is 10 centimeter. Anyway, this ends up giving you a value of 9.15 times 10 to the 6. 10 to the minus 6 mole per decimeter cubed. Sorry, I'm out of space. But I've actually calculated all these. You can just see basically my calculations there on the left. I stopped writing 10 to the minus 6, but all of them are 10 to the minus 6. So I'm not necessarily sure you needed to do this. You could have just graphed the absorbances and then converted in the end back to a concentration, but this question on my slide is asking us to do this, so we can do it. It takes a lot of time though. Convert all those absorbances into concentrations. But it will look something like that. Okay, then draw a graph of this data, including a curve of best fit. I've basically done that on the following slide. So this is what it might look like if we graph concentration in mole per decimeter cubed times 10 to the minus 6 on the y-axis scale. This is concentration. And then time in minutes on the x-axis. I graph this and then try to draw that tangent line as part of the next question. Well, question 3 first just says calculate the average rate of reaction over the observed experiment. I can do that here quickly. I'll use yellow. So the average rate with respect to something, some starting material, is equal to delta C absolute value over delta T. So we can take the difference between when the reaction stops and when it started, So it stops at 1.49 times 10 to the minus 6. And it finishes at, sorry, it started at 9.15 times 10 to the minus 6. And these are mole per decimeter cubed units. You divide that by the time taken. So the reaction finishes at 14 minutes. So 14, but our first data point was at 1, so we should do this. 14 minus 1 minutes. It's really 13 minutes that this change in concentration was observed. So this comes out to 5.89 times 10 to the minus 7 mole per decimeter cubed per minute. We still have the units of minutes there. This does ask for it in seconds, though, right? Well, it doesn't really say. You could probably stop there, but if you want it in seconds, multiply this by 1 minute per 60 seconds. So divide by 60. This will end up being 9.82 times 10 to the minus 9 mole per decimeter cubed per second. It's probably better to report that. 9.82 times 10 to the minus 9. Okay. Now use the graph, estimate the instantaneous rate of reaction at 7.5 minutes. So I've already drawn that tangent line as I showed. I tried to do that there at 7.5 minutes. This point, make a tangent line there. I think I did a pretty good job of that, but now we need the slope of that tangent line. So I'm going to choose my 2 points there. It's better to choose points that are farther away. That's why I'm choosing these two. But my points will be about 3.4 and 5.2. And don't forget, this is times 10 to the minus 6. And then this point on the far right, this is 11.4 and 1.2 times 10 to the minus 6. So should be able to get a slope from those 2 points. So the rate at 7.5 minutes is change in concentration, absolute value over change in time. And this will be y2 minus y1 is 1.2 minus 5.2, both times 10 to the minus 6. And over this time, that is 11.4 minutes minus 3.4 minutes. Don't forget the units. So we will end up with mole per decimeter cubed per minute. This comes out to 5 times 10 to the minus 7. And again, we'd rather have that in seconds. So multiply by 1 minute per 60 seconds. So 8.33 times 10 to the minus 9. Mole per decimeter cubed per second. Okay, so that is the answer to, so that's the answer to number 4. Number 5 then was try to extrapolate to estimate the initial absorbance at t equals 0. So I've already done that by drawing a curve of best fit here. Even though my graph didn't really go before 1 minute, I've continued on that line as best I could to try to follow the path of this graph. And it's going to intercept right here. That looks to me like it's about 11.2 times 10 to the minus 6 mole per decimeter cubed. And then we just need to convert that back into an absorbance to answer this question. So we have absorbance equals epsilon concentration path length. Epsilon was 4,700 decimeter cubed per mole per centimeter. C is what we have here. I'll just do, 11.2 times 10 to the minus 6. And then this is also multiplied by the path length of some centimeters. It was 10 centimeters here. So our centimeters will cancel, our decimeter cube will cancel, our moles will cancel. That's what we want because absorbance is supposed to be a unitless thing. Comes out to about 0.53. Put that in the calculator. But that is the answer to number 5. Again, a range of acceptable answers are probably fine, but that's my guess. And I'm assuming this 10 centimeters does have 2 sig figs. Okay, so done. This is a super long video, but I hope you enjoyed my examples. This really is the kind of thing that appears on IB exams and that you would want to do in your IA if you're dealing with rates. So next time we'll get into a lot more theoretical stuff, the collision theory and how molecules and atoms collide to push chemical reactions forward. And what we might do to control the frequency of successful collisions. That's really what we want to do. All right, thanks for listening. See you next time.